In previous videos, we had talked a little bit about how to find areas of things like parallelograms and rectangles and triangles. How about some of those other figures that we know information about? We know some of their properties, but we haven't found the areas of yet. And one of them is a kite. How do you find the area of a kite? Remember, a kite has two sides that are congruent to each other that are adjacent here, and two sides that are congruent to each other that are adjacent there. The other thing to remember about a kite is that the diagonals are perpendicular to each other. So if you draw a kite and draw in perpendicular diagonals, what you really do is you create four right triangles. The two up at the top are congruent to each other. The two down the bottom are congruent to each other. And so you could actually go through a process where you find the area of each of those triangles individually, add them all together, and something interesting happens here. This is, let's call this A and that B, and this thing over here is C, and that thing over there is D. So look at the triangle on the top right, right? The triangle on the top right has an area of 1/2 times A times C. The one on the top left has an area of 1/2 times A times D, right? In both cases, you're doing 1/2 times base times height. How about the one on the bottom left, right? The bottom left has an area of 1/2 times B times D, right? 1/2 base times height. The one on the bottom right has an area of 1/2 times B times C. Right? Again, 1/2 times base times height. If you want the area of the whole kite, add these four things together. I'm going to pull the 1/2 out of the entire thing. All right? So when I do that, I'll end up with an AC plus AD plus BC plus BD. Right? Those are the four things. All right, let's take the first piece and factor out an A. And then we'll take the other two terms and we'll factor out a B. And then we'll do one more factoring. Let's pull the C plus D out of both terms. That leaves me with an A over here and a B over there. Okay, what have I just created? Don't say a mess. What have I just created? C plus D, isn't that the diagonal that goes this way left to right? So this one here we'll call diagonal 1, and then A plus B is the other diagonal, right? Diagonal 2. So a real quick sketch of where I'm getting the formula for the area of a kite. It turns out that the area of the kite is just 1/2 the product of the diagonals. So the area of a kite, doesn't matter which diagonal you call diagonal 1 and diagonal 2, but is 1/2 the product of the diagonals. And you could do it this way, by finding the area of each of those four triangles and then adding them all together. Or, here's another way of doing it. What if you took these two pieces, right, area 1 and area 2, and then you stacked them up next to areas 3 and 4? Well, if you took this piece here and let's say flipped it up on top, now you've created yourself a rectangle here, right? And then take 4 and flip it up top, and you've got another rectangle, in this case that's shaded yellow. Now, the diagonal 1 is the entire length of the diagonal from this vertex right through that perpendicular spot in the middle all the way to the end. And then this is a symmetry diagonal. So whatever length this piece is over here, that piece will be up there too. So really what you're looking at is half the diagonal. So you could think of it as a rectangle where the area is base times height, except one base is diagonal 1, and the height is half of diagonal 2. Well, I'll move things around and simplify them. Again, you've got 1/2 diagonal 1, diagonal 2. So there's probably other ways of representing the area of a kite as well. But if you know the two diagonals of a kite, then you know the area. All right, how about a trapezoid? Trapezoid, the bases are not the same length. So our formula would have to take into account that we could have two different bases. So you could have a trapezoid that's got a right angle in it, right? You could have a trapezoid that looks like this. And so this base up here is not the same as that base over there. In this case would be your height, and that would be one of the sides. But you could also have a trapezoid that looks like that, where that's one base, that's another base, and then this thing over here is your height. So lots of different options for a trapezoid, and the bases are not the same. The height is not necessarily one of the sides. So what do we do? So then how do we find a general formula for the area of a trapezoid? There's two pictures up here, right? One is my general trapezoid. It's got a base of B1 and B2, and it's got a height. So if I took the one base down the bottom and I formed a triangle out of it with base 1 and the height, and then I took another one up here with base 2 up on the top and the height, I could combine those things together. So instead of having one triangle down here, right, where that's the triangle that has base 1, and you notice the height's the same in both of them. That's one triangle, so I would have a 1/2 times base 1 times the height. And then the second triangle would be that guy up there, where that's the base and that's the height. So I'd have 1/2 base 2 times the height. Well, why not factor out the 1/2 and the height, and I'm left with what? Base 1 plus base 2. So I think of this as 1/2 the height times the sum of the bases. Every once in a while, you'll run across probably an older textbook that connects the midpoints of the sides of the trapezoid and calls that segment the median and defines the median as the average of the bases, right? Base 1 plus base 2 divided by 2, and then looks at the area of the trapezoid as simply the median times the height. So you can do that, but this formula down here that's in blue, that's the more common way of representing the area of a trapezoid as 1/2 the height times the sum of the bases. All right, so let's try to find the area of each of these trapezoids. The first one's a little bit easier, the second one's a little bit harder. This one up here, the information's already given to me, right? If I have a formula for the area of a trapezoid, that goes 1/2 the height times the sum of the bases. Here's my height, right? The height is 4 centimeters. That's the altitudes drawn perpendicular. The two bases are 12 and 16, so I'm going to write in 1/2 times 4, right? That's the height. And then the sum of the bases, 12 plus 16. So 12 plus 16 is 28. Half of 4 is 2. 2 times 28 is 56. And we're in square centimeters. All right, look at the trapezoid that's next to it. The trapezoid that's next to it, and you know it's a trapezoid simply because the question said it was a trapezoid. One base is 2, one base is 8. That's great, but you notice that the height wasn't given. But yet we're given a triangle on either side and told that that's the height. This thing here is a right angle, and this thing here is 45 degrees. Well, if that's true, then it turns out that this piece and that piece are congruent to each other, because what we've got is an isosceles triangle, because if that's 90 and that's 45, that one also has to be 45. Now, if you remember 45, 45, 90 triangles, that makes this easier, but you don't have to know that in order to do this. If that's the case, and this is an isosceles triangle, and that's congruent to that, and the angles down the bottom are the same, that's the same there, they're actually congruent to each other by hypotenuse leg. And therefore, this segment down here, FD, is congruent to this segment here, AE. All right, so if this base is 8 and that piece is 2, I can actually separate that and make that 3 and that 3. So probably I should have told you specifically that AB and BC were congruent to each other, but it turns out it's true that then if this is 3, the height is also 3. Okay, let me run through that again. In this triangle on the left side over here, I've got a right angle at E that's got a measure of 90, and I was told that the angle down the bottom left was 45. So if I know all the measures in a triangle add up to 180, subtract the 90, subtract the 45, and the remaining angle up at the top, this angle up here, has to also be 45. So if you wanted to lay the triangle down like this and say that's your right angle, these two angles are congruent to each other, one of these was my height, and the other one is whatever AE is. Okay. How do I figure out what AE is? Well, if the whole length is 8, and this piece up on the top is 2, this piece in the middle then forms a rectangle. So if the one on the top is 2, the one on the bottom is 2, 8 minus 2 is 6, and so that 6 is divided evenly between the 3 that's on this side and the 3 that's on that side. So all that work was just to figure out that the height was 3. Once I have that, then all I have to do is throw it in my formula. 1/2 the height times the sum of the bases. So I get 1/2 times 3 times 10. Half of 10 is 5. 5 times 3 is 15. Okay, so concentrate your effort for this one on figuring out that height based on the fact that if that piece on the top is 2, that little piece EF on the bottom is 2, the whole length is 8. 8 minus 2 is 6. And then if those two pieces are divided evenly, half of 6 is 3. All right, how about regular polygons? Suppose you wanted to find the area of a regular hexagon. Well, if you divided that regular hexagon into 6 triangles, you're going to need the altitude of one triangle. The altitude, remember, goes from the vertex perpendicular to the base. Well, there's a name for that altitude. It's actually called the apothem, but sometimes people mispronounce it as the apothem, which sounds like a little furry creature that crawls across your front lawn. But no, this is the apothem. It goes from the center perpendicular to one side. So if you wanted to find the area of one of those triangles, you would do 1/2 times base times height. So 1/2, the base is the side of the triangle, right? Or in this case, the side of the hexagon, and the height is the apothem. So 1/2 times A times S. And you would do that as many times as you have sides. So that's one side. That would be another side, third side, fourth, fifth, sixth. So yeah, I could multiply it by 6. But in this case, you realize that if I do 1/2 times A times S plus 1/2 times A times S, by the time I get done doing 1/2 times A times S 6 times, I'll have really done 1/2 times A times 6 of those S's. Well, isn't 6S just the perimeter of my hexagon? So I'm going to make a more general version of this, which is that the area of a regular polygon is 1/2 times the apothem times the perimeter of the polygon, right? Which is actually going to show up in the next slide. All right, so in general, 1/2 AP. A is the apothem, P is the perimeter of a polygon. And if you want to find then the area of that regular polygon, 1/2 times A times P. You may have to work a little bit, and we'll get to some examples, I think, in future sections where you have to work a little bit to find out what that apothem is. But in general, 1/2 AP will give you the area of a regular polygon. Now, I don't know if you've seen this before, but what if I were to take the sides of a regular polygon and increase the number of sides? So I could go from, let's say, a rectangle to or square rather, to a regular hexagon, to a regular decagon, and keep going and keep going. Eventually, what is it going to look like? If I keep increasing and increasing and increasing, then eventually, if I get a regular 20gon, a regular 40gon, a regular 100gon, it's going to start to look like a circle. Okay, add enough sides in here, and this wheel, as all these spokes, is going to start looking like a circle. So the area then becomes pi r squared, right? The apothem becomes the radius, right? If you do it enough times, then that radius and that apothem become eventually the same thing. And then the perimeter of that circle becomes 2 pi r, right? That's the circumference. So 1/2 times A times P turns very quickly into pi r squared. So you can do one of these little experiments, keep taking the sides and adding them and adding them and adding them. That's another way to explain the area of a circle. How about this way to explain the area of a circle? All right, start with your circle. If the whole circumference is 2 pi r, then half of the circumference is pi r. And that's why it says down the bottom here pi r, because that's half the circumference of the circle. Okay, take that and split it apart. And take each of these wedges and take the light blue wedges, and then in between those light blue wedges, put your dark blue wedges. So each of these are then half of the circle, right? The light blues are half the circle. The dark blues are half the circle. Basically, what I've come up with is a rectangle where the base is equal to pi times r and the height is equal to r. Well, if I multiply those together, I end up with pi r squared. So there's another way of taking your pieces of a circle apart, turning them into a rectangle, and now you've explained the area of a circle in yet another way. Okay, and you can do these with physical models too, right? Take things and cut them apart. So here's my question. I've got two pizzas. 14-inch pizza has the same thickness as a 10-inch pizza. How many times more ingredients are there on the larger pizza? Now, the first thing you might talk to classes about is distances. Are we talking about the radius being 14 inches or the diameter being 14 inches? And yes, I've had these conversations, and you get some interesting answers. A 14-inch pizza has a 14-inch diameter, right? In other words, on your pizza, it's 14 inches from end to end. It's not 14 inches from the center to a point on the outside. Otherwise, your pizza would be 28 inches wide. So if you ordered like a 16-inch pizza, that thing would be 32 inches from end to end. And depending on what kind of house you have, it may not fit through the door without tilting it. So we are talking about 14 inches being the diameter, not the radius. Okay. So let's find the area of each pizza. So let's do first the one with a radius of 5, right? Because the 10-inch pizza, if that's the diameter being 10, then the radius is 5. The area of a circle is pi r squared, or in this case, pizza pi r squared. So my area is going to be 5 squared times pi, so 25 pi. Okay. How about the one with the radius of 7? In that case, area is equal to pi times 7 squared, right? Because if the diameter is 14, then the radius is 7. So here my area is 49 pi. Look at those two values. You realize the 49 pi is almost double the 25 pi. I could actually take the two of them and divide them, right? I could take 49 pi and divide it by 25 pi. And 49 divided by 25 is real close to 2. Right, 1.96. So 1.69 times as much. Which is kind of interesting, right? Because sometimes one pizza is like $7.99 and then the larger one's like $10.99. There's not much of a difference in price, even though ingredients-wise, you're getting twice the area in the bigger pizza as you are in the smaller pizza. Like, what if you want to take a piece of pizza? Now we're all getting hungry because we're talking about food. So instead of taking a slice of pizza, perhaps you're taking a sector of the pie. A sector is a fraction of the area of the whole circle, or in this case, we're talking about pizzas, so a fraction of the area of the whole pizza. If you cut your pizza up into 6 slices, then each of those central angles are 60 degrees, meaning that you're eating 1/6 of the pizza. If you slice into 8 slices, then each of those slices are 1/8 of the pizza. So I need to know how much of the whole pizza I want. In this case, my central angle will tell me that. Take that central angle and divide it by 360. So for example, if theta is 60 degrees, then 60 over 360 is 1/6 of my pizza. If you, let's take this out of pizza for a second, if this was just some drawing and theta was, let's say, 50 degrees, and the radius were 6, then the area of that sector over here would be 50 over 360. That's how much of the whole circle I want, and the area formula is pi times r squared. So pi times 6 squared will give me whatever 36 times 50 times pi over 360 is, right? And you can simplify that, and that would be the area of that sector. So the area of a sector is just a fraction of the area of the whole circle. If you can tell me what the area of the whole circle is, then use that central angle out of 360 to find the area of just that sector. All right, let's take a look at one more problem, and we are done. I thought this was kind of interesting. I think I stole it from your book. You got a red circular glass inside of a right triangular window, and you want to know what the radius of that circular glass is. In order to do this, we're going to have to bring in a little theorem here, which tells us that if we take a circle and we draw tangents on the outside of the circle, a tangent intersects that circle just once. Right, so here, I draw this out. It intersects exactly once. It turns out that this distance here and that distance there are the same from the point on the outside to what we call that point of tangency. And that's going to become important when we draw out this picture. You notice that that triangle is tangent to the circle at every point. So it's tangent over there, is tangent over here, and over there as well. So it intersects exactly one point. That line doesn't go through the circle. It touches that circle once. All right, so knowing that, I'm going to call this distance from the vertex to that point of tangency x. Well, if that's true, then that piece is also x. All right, let's come down the bottom. I'm going to call this piece over here y. If this distance here is y, then that distance over there is also y. Now, I'm sort of working my way into a corner here. If I know the whole side is 4 and that piece over there is x, then that piece down there has got to be 4 minus x. I'll use the same logic on the bottom. If that whole side is 3 and the one piece is y, this has got to be 3 minus y. All right, so what information do I know now that can help me? Look at the hypotenuse of the triangle. The hypotenuse of the triangle has an x and a y, and it adds up to 5. Right? So that x and that y, we know add up to 5. The other thing we know is that this piece over here and that piece over there are actually the same length. Right? Those are both tangent segments that are drawn to that circle. So here, let me do a little work on the side here. That 4 minus x is equal to 3 minus y. All right, let's try to get everything over to the same side. So I'm going to add an x to both sides, and I'll get 4 equals 3 plus x minus y. And then I'm going to subtract a 3 from both sides, and I get 1 equals x minus y. So if x plus y is 5, x minus y is 1, oh my goodness, I got myself a system of equations to solve. And it solves itself fast, right? The y's go away, and I'm left with 2x is equal to 6, or x is equal to 3. Okay? If x is equal to 3, then I can go back and I can find y. Right? If x is equal to 3, then y must be equal to 2. It should then turn out that these numbers are the same, right? 4 minus 3 is 1. 3 minus 2 is 1. And my last bit of the problem is to realize that inside that piece on the bottom, unfortunately, I only have one color here, and it's red. That piece on the bottom where I have that circle, if I went from the center to a point on the outside here and center to a point on the outside there, what I've actually made is a square. So if those two sides are 1, those two sides are also 1, and these pieces here, that's the radius. So this is a pretty complicated problem. This is something more in-depth than you're going to see on a test. But I thought this was kind of a fun problem because if I introduce just that one concept of the two tangents, then from there, you can actually solve the rest of the problem. And that's it.